Okay, may I start, David?
Okay, yes. So I'll give you the 5-minute warning.
Thank you.
Right before you start, sorry, right before you end, and then I'll introduce you now. So the next speaker is Oscar Diaz from the University of Southampton, and he's going to tell us about new super young Mill phases at finite chemical potential. So go ahead.
Thank you, David. So first of all, let me thank you for this kind of opportunity to be here in this workshop. In particular, I would like to thank two of the organizers, Anosh and Masanori, with whom I traded most of the emails. And today, what I want to describe, what I want to tell you about is about new super young Mill phases at finite chemical potential. And by this, what I mean is that I will construct solutions that are asymptotically ADS5 cross S5, so solutions of type 2b supergravity that are asymptotically ADS5 cross S5, and therefore, via the original ADS-CFT correspondence, they will be dual to thermal phases at finite chemical potential in the dual super young Mills field theory. So this is based on work that I have done with George Santos, who is a professor at Cambridge, and probably many of you know him about, so he needs no further presentations, and with Prahar Mitra, that is a postdoc at Cambridge, and he is a brilliant postdoc that should now be starting to apply for permanent jobs or for tenure track jobs, and that I highly recommend. If for some reason you turn out to come to see his CV. So let me move on. And in this first slide, I want to tell you something that everybody in this audience certainly knows. Nevertheless, let me go through it just to set up the context of this talk. So in its weakest form, the original ADS5 CFT duality tells us that type 2b supergravity, so type 2b supergravity on ADS5 cross S5 with radius L and n units of the self-dual 5 form flux on the S5 is dual to large and strong Toft coupling limit of n equals to 4 super young Mills theory with gauge group SUN. And in particular, in this duality, we know that thermal states of n equals to 4 super young Mills at finite temperature and with chemical potentials and energies of order n square that live on the Einstein static universe, so R cross S3, which is basically this boundary here, are dual to asymptotically global ADS5 cross S5 black holes on type 2b supergravity with Hawking temperature T and chemical potentials. And in the rest of this talk, I would like to highlight that I will always be working with global ADS5, not planar ADS5, which means that the dual theory lives on the Einstein static universe with the S3 on the boundary, okay? Now, for this duality, it is extremely important that we try to find all possible black holes of the theory and map them to thermal states on the dual super young Mills theory, because this will allow us to identify the dominant phases as saddle points in the associated thermodynamic ensembles we are interested on. And in particular, this program is important if we want to reproduce microscopically the Hawking-Bekenstein entropy of ADS black holes. Indeed, already more than 20 years ago, Strominger and Waffe, or starting with Strominger and Waffe, we have already managed to derive the microscopic entropy of asymptotically flat black holes. But the program for asymptotically ADS black holes, the program of deriving microscopically the entropy of asymptotically ADS black holes is far from being complete. And if you are interested on this particular topic, I would recommend Benini's review talk at Strings 2022. Moreover, another motivation to complete this program of trying to find more black hole solutions that are asymptotically ADS5 cross S5 is because this program might help us understanding an intriguing puzzle of SO6 gauge supergravity, namely the most general supersymmetric black hole that is known so far in this theory is what we call the Konduri-Luchetti real black hole. that extends the Gutowski real black hole. And what is interesting is that this black hole has only 4 independent parameters. Well, actually, it would be a 5-parameter solution, but then we have the BPS constraint that reduces the number of independent parameters into 4. However, we know that the most general supersymmetric solution, already including, therefore, this BPS constraint, should be a 5-parameter solution, not a 4-parameter solution. And actually, this is also the counting that comes from the CFT perspective. So we should ask, where is the missing gravitational parameter that we need? Okay, again, trying to find more black hole solutions of type 2b supergravity should help us identifying this missing gravitational parameter. Therefore, in the rest of this talk, I want to identify new thermal phases with a finite chemical potential. And in particular, I'm interested in solutions in phases that the microcanonical ensemble, as we will see next. Before doing so, let me just give a brief overview of some known solutions of type 2b supergravity. So to start with, again, this is something that everybody in this audience knows very well. Type 2b supergravity has several fields, namely the metric, the dilaton, an axion. Then it has the Neveu-Schwarz 2-form tensor. It has the Ramon-Ramon 2-form potential, and a 4-form Ramon-Ramon potential that sources a self-dual 5 forms field strength. And then there are also the fermionic superpartners. Now, in this theory, we already know some solutions. For example, in particular, I'm interested in solutions that only have the metric and the self-dual 5-form turned on. And in this case, of course, the simplest solution we can have is global ADS5 cross S5, the Schwarzschild black hole. That, as we know very well, is the direct product of an asymptotically global ADS5 black hole times an S5 sphere, okay? Everywhere, not only at the boundary, but everywhere in the bulk. And in particular, the horizon topology of this black hole is S3 cross S5. And we know very well that this black hole can exist. There are 2 types of Schwarzschild black holes. There are the small and the large black holes. And Witten already in 98 told us that there is also an associated Hawking page phase transition that is dual to the confinement-deconfinement phase transition in the CFT. In addition to these black holes, another example of black holes that are asymptotically global ADS5 cross S5 are what we call localized black holes on the S5. So what happens in this case is that we have here 2 scales, the horizon radius and the radius of the S5. And we can have a situation where there is a large hierarchy between these 2 scales. So the horizon radius can be much smaller than the radius of the S5. And when this happens, very much like in the Gregory-Laflamme system that Poffiger has reviewed this week for you, what we should expect is that an instability should appear and the system should localize. In this case, what happens is that the instability breaks the SO6 symmetry of S5 down to SO5. And therefore, the black hole localizes, for example, at the north pole of the S5. So these black holes will have not S3 cross S5 horizon topology, but instead they have S8 horizon topology. This means that instead of being uniform along the S5, these solutions will depend on the polar angle when you go from the North Pole to the equator. So this motivates us to start to try to find even more super young Mille phases. And in order to do that, of course, we would have to solve the equations of motion of type 2b supergravity. But this is very challenging. So trying to give baby steps instead of trying to find the most general solution of type 2b supergravity, we can try to look to dimensional reductions of type 2b supergravity, in particular along the S5. And in this case, we find that there is a dimensional reduction of type 2b along the S5 that yields n equals to 8 gauge supergravity. And this supergravity is believed, although it is not proven, to be a consistent reduction of type 2b on ADS5 cross S5. In this n equals to 8 gauge supergravity, the 10-dimensional type 2b fields are equivalently encoded in the 5-dimensional field content of n equals to 8 supergravity. That includes the graviton, 15 gauge fields, 12 other gauge fields, and 42 scalars, plus the fermionic superpartners. However, we might only be interested on type 2b supergravity that only has the metric and the self-dual 5 form turned on, because these are the two fields that are the most relevant for ADS-CFT, namely because they are the ones that are required to source the D3 branes. And it is known that type 2b can be dimensional reduced along the S5 to produce what is called the SO6 gauge supergravity, when only these two fields are turned on. Of course, this SO6 gauge supergravity is itself a consistent truncation of n equals to 8 supergravity that I described above, when we set many of its fields to 0, namely when we set 22 of the scalars to 0 and 12 to form gauge potential to 0. So in the end of the day, we are just left with the graviton, 15 gauge fields, and 20 out of the 42 scalars. But these are still too many gauge fields to be able to solve the equations of motion. So what we can try next is to, again, in this spirit of giving baby steps before trying to solve the most general problem, we can think on another consistent truncation of SO6 gauge supergravity, this time down to the Cartan subgroup of SO6 that has 3 gauge fields associated with it. And this is what we can call U1 to the cube gauge supergravity. In this case, we have much less fields turned on. So we have the graviton, we have 2 neutral scalars, we have 3 gauge fields, and we have 3 complex scalar fields that are minimally coupled to the 3 U1 gauge fields. All these scalars, both the neutral scalars and the complex scalar fields, they have a mass that saturates the BF bound. And moreover, the complex scalar fields, the 3 of them have a charge that in ADS units is equal to 2. Now, the action of this U3 gauge supergravity is written here, and I promise this is the only formula that I will have in this presentation. Basically, we have the Einstein-Hilbert term, then we have a kinetic term for the neutral scalar fields, we have the usual Maxwell field for the 5-dimensional form, then we have also a kinetic term for the charge scalar field, and we have a potential that depends on a potential for the scalar fields, for the neutral and charge scalar fields. There is also a Chern-Simons term, although for the static solutions that I will describe next, this term vanishes. Okay, so this is the theory I want to study in more detail in order to find its most general black hole solutions. And remember that this gauge supergravity is a consistent truncation of type 2b on ADS5 cross S5, where only the graviton and the self-dual 5 form are turned on. Okay? Now, the equations of motion for this gauge supergravity are still very complicated. So we want to reduce the complexity of the problem even further. In order to do that, I will focus my attention on 3 truncations of this theory, namely a truncation where the 3 gauge fields are the same, and therefore the 3 complex scalar fields are also the same. Another truncation is a truncation with a single charge where only one of the gauge fields is non-vanishing, but the other 2 vanish. And finally, the truncation with 2 equal charges where one of the gauge fields and one of the complex scalar fields vanishes. Okay? Actually, this and this, the first and the third truncation, they are expected to represent the generic case where we have arbitrary charges. Okay, and in this talk, due to the constraints we have with time, I will focus my attention on this truncation here with two equal charges. So this is the phase diagram of solutions that I will describe next. And the first question that we might ask is, what are the solutions of this theory when the complex scalar fields vanish? And these solutions are known. These are the so-called Cvetic-Lu-Pope solutions that were already found in 2004. So these are solutions where the charged scalar fields vanish. But there is still the graviton present, there are still the neutron scalar fields present, and the 3-gauge fields are also present. And these 3-gauge fields, they source the 3 electric charges of the system. These Cvetic-Lu-Pope solutions, they can be thought as the Reiser-Nordstrom ADS5 black holes of the theory. However, in this case, they are not really Reiser-Nordstrom because we also have the neutral scalar fields supporting these solutions, so they are not vanishing. Actually, in the case where the 3 electric charges are the same, it just happens that the 2 neutral scalar fields actually vanish, and the Cvetic-Lu-Pope solution is identically equal to the Reiser-Nordstrom ADS5 solution. As I told you before, I want to concentrate on the 2 equal charge truncation, and I can draw a phase diagram where on the vertical line I plot the charge, the dimensionless charge of the system, and on the horizontal line I plot the energy, the dimensionless energy of the system. I represent here as a dashed black line the BPS limit, where the energy is equal to 2 times the charge, and then all this green area describes the region where the CLP black holes exist. So they exist from 0 charge all the way up to a maximum charge that is given by this purple line. And this purple line is the solution, is what we call the extremal CLP solution. So this is a solution that is singular because the entropy vanishes, okay, along this purple line. However, the temperature does not vanish. The temperature is finite. Okay. Okay, but these are the solutions with no charge scalar field. But next, what I can do is I can ask what happens now if I perturb this CLP black hole with one of these charge scalar field perturbations. Okay, and this is what I want to do next. Okay, so I want to take these CLP black holes that I will call the bold black holes because they have no charge scalar field, okay? And I want to perturb this black hole with a charge scalar field that has the following Fourier decomposition. Since time is a killing vector of the CLP solution, I can do a Fourier decomposition in a long time, which introduces the frequency of the perturbation, the frequency omega of the perturbation. Then I plug this perturbation in the equation of motion for the charge scalar field, which is the Klein-Gordon equation of the system in the CLP black hole with appropriate boundary conditions. And these boundary conditions are that I want the solution to be asymptotically ADS5, and I want the solution to have only ingoing modes at the horizon. And I look for the frequencies. The frequencies will be quantized by these boundary conditions. And I look for the frequencies and I compute the real part of the frequencies and I compute the imaginary part of the frequency. And we conclude that the system is unstable when the imaginary part of the frequency is positive. And what I'm doing in this figure here on the top is I'm fixing the charge of the black hole to be 1. And I'm precisely computing, the orange line computes the imaginary part of the frequency as the energy along the horizontal axis increases. And what I find is that to the left of this point that I'm calling beta, we see that the imaginary part of the frequency is indeed positive, which signals an instability. So this point beta in particular is what we call the onset of the instability. Now, I did this for a particular charge, but I can now do it for the other charges of the system, and I will find the set of beta points that will describe the onset of the instability. Actually, I can also solve directly for the onset of the instability by setting the frequency to be 0, since I see that at this point beta, where the instability kicks in, I see that both the real part and the imaginary part of the frequency vanish, okay? This is an alternative way to get the onset of the CLP instability. And by doing one of these two methods, I find this blue curve on the plot that I already had before, which plots the charge in the vertical axis as a function of the energy. And so remember, the CLP black holes exist in all this green area, okay, all the way up to extremality. And now what I find is that CLP black holes that are above this blue curve, they are unstable to the condensation of a charge scalar field, okay? So in particular, for charge equals to 1, which is the one that I looked at on the top, I identify here my beta point that gives the onset of the instability. And then the instability at constant charge exists all the way up to the BPS limit, actually, okay? Moreover, I should say that the theory also has a supersymmetric solitum, which is this black dashed line that is precisely, because it is supersymmetric, it has a charge that is precisely given by the energy divided by 2. This soliton also has a non-trivial or a finite charge scalar field condensate, or a charge scalar field VEV. And we can also construct this solution numerically. Okay. Now, what we have just seen is that we took CLP, the CLP black hole that has no charge scalar field. We studied perturbations of the charge scalar field on top of it, and we saw that the system becomes unstable above this blue line. Now, in the context of perturbation theory, what I have done was that I analyzed the linear order of perturbation theory, where the charge scalar field condensates. Now I can go to higher order in perturbation theory, and at higher order in perturbation theory, at second order in particular, I know that the charge scalar field should back react on the other fields, namely the graviton, the U1 gauge fields, and the neutral scalar fields, okay? And I should, at the full nonlinear level, at second and higher order in perturbation theory, I should be able to construct airy black holes that will now have a charge scalar air, which was not present in the case of the CLP black hole. And actually these airy black holes, they should, in the phase diagram of energy as a function of the charge, they should exist above the onset line of the instability of the CLP black hole. They should bifurcate from there. So my next task is to construct these airy black holes. In order to do that, we will have to solve a coupled system of 5 nonlinear ODEs subject to the appropriate boundary conditions, namely it has to be regular at the horizon, it has to be asymptotically global ADS, meaning that the graviton field must approach the Einstein static universe. And we will impose an homogeneous chemical potential. And for the scalar fields, we will require that there are no sources. Remember that both the neutral and the charge scalar fields, they are saturating the BF bound, and therefore the two asymptotic decays of the scalar fields include a log term, and I want this log term gives me the coefficient of this log term gives me the source of the fields, and I want to kill the source of these fields, and then I will just read the VEBs of the fields. In order to compute the thermodynamics of this system, I use holographic renormalization. Now, if I do this, what do I find? So here I'm plotting again the phase diagram that we saw already before, namely in the vertical axis, I have the charge, the dimensional charge of the system. On the horizontal axis, I have the energy. The green area, as you remember very well, is the CLP black hole. You remember that the CLP black hole was not extending all the way up to the BPS solution because there was an extremal solution. It was stopping here. There was here an extremal solution. That was singular because the entropy of the CLP black hole was going to 0. Then I found that this CLP black hole should be unstable above this blue curve. And now what I found non-linearly is that in this red area that extends from the blue curve all the way up to the BPS black dashed curve, there are airy black holes. So these airy black holes actually fill a region of the phase space that was otherwise empty, which would not be consistent with what we know from the dual CFT. From the dual CFT, we would expect thermal states all the way up to the BPS limit. But the CLP black holes were not providing these states. It's the airy black holes that provide these states. Now,
Oscar,
these airy black,
5 minutes.
yes, 5 minutes. Okay, thank you. Okay, thank you. Now, these airy black holes, a particular property of these airy black holes is that they are singular in the BPS limit, meaning that the entropy or the horizon radius goes to 0 as we approach this BPS limit. Nevertheless, their temperature is finite when we approach the BPS limit. And moreover, and this is perhaps a surprise, although not that much because the solution is singular, it's not smooth in the extremal limit. And the chemical approach is one, which is something that we would expect for a solution that is approaching the BPS limit. Okay? Very well. Another thing that we can ask is, what is the limit? What is the BPS limit in more detail? What is the BPS limit of the airy black holes? Well, we can argue that, well, first of all, this is a singular limit. So the entropy goes to 0, which means that the horizon radius goes to 0. In this sense, we can say that the limit, the BPS limit of the airy black holes is the soliton that also does not have an horizon. Okay. But on top of that, we can also compute the charge scalar field VEV, expectation value, for the airy black hole as we move along the line of constant charge, for example. And this is what these blue dots represent. It's a line of constant charge airy black holes. And then I approach the soliton or the BPS limit. And I find that the VEV of the charge scalar field of the airy black hole approaches the VEV of the soliton. Now, this soliton exists for any energy, so there is no Chandrasekhar limit. And this is very unique to the two charge case. For the 3 equal charge case, and actually for the arbitrary 3 charge case, okay, we expect that the soliton exists only up to a certain maximum energy, which is the Chandrasekhar limit. Now, you might ask, okay, so far I have been discussing solutions that are static. What happens when I add rotation? In order to do that, I will consider the special case for this talk where I put the 2 possible angular momenta equal to J, because this produces a system of equations that is homogeneity 1, meaning that I just have to solve 10 coupled nonlinear ODEs. Now the BPS relation, of course, gets changed because now there is also a contribution coming from the angular rotation, from the angular momentum. And what I'm going to do is I will work at finite temperature and decrease the temperature as much as I can towards 0. Because in the end of the day, what I want to find is evidence for the existence of novel supersymmetric black holes. Now, in this case with rotation, CLP black holes also exist. They are here in this green area. So here I'm plotting the same phase diagram that we had until now, but now at fixed J. J is equal to 0.1 here. On the vertical axis, I still have the charge. On the horizontal axis, I still have the energy. I still have the BPS limit, the black dashed line here. And the CLP black holes still exist only up to an extremal solution, which is this purple line. They are still unstable above this blue curve, okay? Now, this blue curve extends all the way to this point A. This point A that is precisely at the BPS limit is a supersymmetric black hole without air that is known as the Gutowski real black hole. It's a 1 per meter solution. So if I put a third axis that is the angular momentum, you see that this point A will become a line, okay? So the most general Kunduri-Luchetti real solution is the one where we have 3 arbitrary charges and 2 arbitrary angular momentum, and therefore it's a 4 per meter solution. But here I'm looking to the sector of 2 equal charges and with equal angular momentum. And now what happens when we add this rotation is that we have airy black holes from this region, from the onset curve all the way up to the BPS limit. And what is interesting now is that, unlike in the static case, the BPS limit of the airy black hole sorry, the BPS limit of the Airy black hole, this time has finite entropy. So it's a known singular limit where the temperature in particular also goes to zero. In the static case, it was going to a finite value. And the chemical potential also goes to zero in this BPS. So basically we have found novel evidence for the existence of a novel supersymmetric black hole that this time has a charged scalar field condensate on top of it. It has some hair. And this can be, so what I'm saying is that now we have, besides having this Gutowski real black hole, we also have this line here of supersymmetric black holes. The difference is that here we have a non-trivial charge scalar field on the solution, and in this Gutowski real limit, the charge scalar field VEV vanishes. Okay, so we might have found the missing gravitational parameter. And therefore, to conclude, let me just say that we have found static Airy black holes. And by the way, in all these cases that I have been discussing, both in the static case and in the rotating case, the Airy black holes, when they coexist with the CLP black hole, which is, for example, in this region, not for example, is this region here between the blue line and the purple line. So for a given energy and for a given charge and for a given angular momentum, the Airy black holes always have more entropy than the CLP black hole. So if we think, so they dominate the microcanonical ensemble. And in particular, if we do a time evolution where we start with CLP, this region, and we let time evolve, it's natural that the system will condensate the charge scalar field around the horizon and will evolve towards an Airy black hole, which will have more entropy. And we should try to, any microstate counting of the entropy of the black hole should reproduce the entropy not only of the bold CLP black holes, but also of the Airy black holes. So these Airy black holes that dominate the microcanonical ensemble, they are really important for the program of deriving the microscopic entropy of a black hole. Okay? So, and probably I should stop here. Let me just say that all these black holes that I have described until now, including the Gutowski real ones, only preserve one of the supercharges. So they are 1/16 BPS solutions. There are some studies that suggest that the system should also have solutions that are 1/8 BPS solutions. And we suspect that these solutions that preserve two supercharges might be Airy solutions. So we are also trying to find them, and we already have some evidence that this is indeed the case. And I should stop here. Thank you, David, and my apologies.
No, thank you, Oscar. Any questions?
Thanks for a very nice talk. I got a little confused. So you began the talk by saying that you were missing some BPS solutions. I think you expected 5 parameter worth, and you had 4. And
Correct.
now, have you found all 5 parameters worth or not? I mean,
yeah, we found evidence that this extra parameter might well be, this VEV, if you want, of the charge scalar field. You see that I was. Can you still see my screen?
Yeah, we can.
With the PDF. Thank you very much. So you see, in this particular truncation, the BPS, the known BPS solution, the Gutowski real BPS solution, is this point here, okay, at the BPS line. Now, this is at constant angular momentum. So if I draw a third axis, which is the angular momentum axis, you see that this point will become a line, right?
Yeah.
Now, what I'm saying is that this line is a line of supersymmetric solutions that have no air, where the charge scalar field vanishes. Okay. Now, what I'm saying is that if you are willing to add the charge scalar field to the solution, and you should be, right, because it comes from the consistent truncation of type 2b supergravity when you just have the graviton and the self-dual 5 form. Okay. what you'll find is that there are new solutions, supersymmetric solutions that extend this point to this line along the BPS line.
Right.
You
right.
see? So the
Yeah.
solution, instead of being a 1 parameter solution, becomes a 2 parameter solution.
Right. Right.
Okay, in that sense, this might well be the extra.
But, you seemed, if I may say, a little tentative. So I was wondering, do you expect additional solutions? For example, you mentioned with 1/8 supersymmetry that you haven't found yet. Is that your expectation? Or?
So this comes. It's not from a gravitational study. That comes from a pure CFT study. Okay, namely, some studies that are ultimately summarized in this work here, from Choi Kim Kim and Nam Gong Gong. Okay, from looking to what is called the McDonald index, in a certain limit, in a limit where the electric charge, the third electric charge plus the second angular momentum vanishes, they seem to find on the CFT side evidence for the existence of thermostates that preserve two supersymmetries instead of just one.
I see.
So one thing, but this on the gravitational side we do not have this solution.
Okay.
We do not have such a solution. The most general one we have is this Kunduri-Luchetti real solution. So one possibility, of course, is that this solution exists in the sector where we turn on the charge scalar field. It could also be that it exists in an even more complicated sector where besides the charge scalar field, we also have to turn on, some of the other fields. You remember, I was setting other scalars to 0, many other scalars to 0, many other gauge fields to 0, right?
Yes.
But if we have some luck, it will already be in this simplest sector where we just add these charge scalar fields.
Okay. Thank you. Thank you.
Thank you. I'm going to cut the conversation mostly because people need coffee and we're a little over time. But thank you so much, Oscar.
Thank you, David. And it was good to see you again. Bye-bye.
Hopefully next time it's in person. Okay.
Indeed.
Take care, Oscar.
Thank you.